All right, so 6-4. We're going to talk about 6-4, and right now I'm in your packet on page 127. I'm going to jump around a little bit, but right now we're on 127. Fill in the table at the right. 2 to the third, 2 to the second, 2 to the first, 2 to the 0, 2 to the -1, 2 to the -2. If you plug this in on your calculator, you would get 1 over 4. 2 to the -3, you'd get 1 over 8, which makes sense what we talked about before. 2 to the -3, if we want to make that exponent positive, we'd have 1 over 2 to the +3rd. 2 to the -2 would be 1 over 2 to the +2. 2 to the -1 is 1 over 2 to the +1. Okay, so those all work out. What do you notice about an exponent raised to the 0 power? Well, anything raised to the zero power, unless your base is also 0, you're going to get 1. What do you notice about negative exponents and compared to positive exponents? Okay, so what we're going to say is that a power with a negative exponent moves the power to the denominator, if it's in the numerator, to the denominator. I'm going to say or to the numerator if it was in the denominator. If it were to start out in the denominator. So it moves it from the top to the bottom or bottom to the top. And when you do that move, the exponent of your power turns positive, becomes positive. Okay, so I know I mentioned this the other day, but x to the negative n, this entire exponent is going to move to the denominator, and the exponent turns positive. Okay. In the same way, if it started out as x to the -n in the bottom and you wanted to move it to the top, well, that would move to the top, and then you get x to the +n. Okay, just the exponent changes sign when you move the entire power to the bottom or from the bottom to the top, provided that your base is not also 0. Okay. Now, the key for a rational exponent, remember what a rational exponent is: a number that can be written as a ratio of integers. So when you have an exponent that's a fraction, so basically a ratio, so something like x to the 1 over n is equal to the nth root of x. Okay, so let's think about what that means. That would mean 2 raised to the 1/2 would equal the nth root, in this case, the square root of 2. Okay, so if we think about what that means, what's the square root of 2? On the calculator, square root of 2 is roughly 1.14 or so. Let's do that. Square root of 2, and I'm going to put a decimal there, 1.141. 1.141. So let's see if that makes sense in terms of this. 2 to the 0 is 1. 2 to the 1 is 2. So 2 to the 1/2 should be somewhere in between. Okay. And this is really a table. If we were to graph this, it looks like, let's just do a new graph. Two to the x, 2 raised to the x. Okay, so if we do a trace, menu 5, 1, we can see when x is 0, y is 1, when x is 1, y is 2. When x is 1/2 or 0.5, we're going to get 1.141. I don't know if you can see this very well, but you could do this on your own calculator. You can see that that works. 2 to the 1/3 is now the cube root of 2. So whatever is on the bottom, that becomes the root. Now, what does a cube root mean? It means what number multiplied by itself 3 times in a row gives you that number. So it's a little hard to look at it here. But if we know what our perfect cubes are, remember our perfect cubes from the other page. Got 2 cubed is 8, 3 cubed is 27, 4 cubed, these are all perfect cubes. So to undo a perfect cube, you'd take a cube root. That means the cube root of 64 would equal 4. Cube root undoes that perfect cube. So it takes 4 cubed. When you cube it, you get 64. When you uncube it, you're back to 4. Cube root uncubes something. Okay, so it's really asking what number multiplied by itself 3 times, not like a square root. A square root, square root of 25, you're saying what number multiplied by itself twice gives you 25. And that's 5 because you're taking the square root of 5 times 5. Perfect cube, what number multiplied by itself and then by itself again gives you 64. Okay, so just like the cube root of 27 would give you 3. Cube root of 8 would give you 2. You basically uncubed 8, you're back to 2. Uncubed 27, you're back to 3. Now, if you uncube 2, 2 is not a perfect cube. So you're thinking about what number multiplied by itself and then multiplied by itself again gives you 2. So that's going to be a decimal. Okay. So if we look at this on the calculator, we do, we're still in trace mode. Let's do 1/3. We get 1.26 roughly. Okay. So just for fun, let's do 1.26 times 1.26 times 1.26. We should get something that's right around 2, and we do. Okay. So now, this is key for understanding how a rational exponent, a power with a rational exponent, compares to a radical. Okay. Now, you might also have something in the numerator. You might have x to the m over n. There's 2 ways to think about that. You could think of this as x to the 1 over n raised to the m, or you can think about it as x to the m raised to the 1 over n. Think about what that means. We've got a power of a power. When you have a power of a power, you leave the base alone and you multiply the exponents. M times 1 over n gives you m over n. Now, did we have to do this first and that this? Remember, multiplication is commutative. We could have had x to the m raised to the 1 over n. Because again, you have a power of a power, multiply the exponents, m times 1 over n. That works also. So let's think about what this means. Here, you have the x to the 1 over n, which we know is this. We have the nth root of x, and we're raising that to the m. And here we have x to the m, and that's our base, and we're raising that to the 1 over n, which means we're taking the nth root of this thing. Okay? These 2 things are equal. You can do it either way. These mean the same thing. They don't look the same, but they mean the same thing. The nth root of x to the m, or the nth root of x to the m. You can exponentiate that x first or second. So that's kind of interesting. Okay, and we're going to go over some examples of this. This looks like, oh, that's a neat property. Now, when you apply it, it gets a little more confusing. Okay, now before I go on to another page, I'm actually going to, you don't have this in your packet, but I made a few problems just to understand going back and forth when you have a rational exponent versus a radical. Sometimes you're going to simplify, and it says leave your answer as a power with a rational exponent. Sometimes it's going to say leave it in radical form. So here, I'm going to give you some examples. I'm going to go through these fairly quickly because a lot of them are fairly simple examples, but there's a lot to them. Okay, transform to radical form and simplify. So 3 raised to the 5/2. The number on the bottom, you're taking that root. Here it's a square root. Square root. Now you could put a little 2, tuck a little 2 in there, but square roots are so common we usually don't. the square root of 3 raised to the 5th. I could do the square root of 3 to the 5th, or I could have done the square root of 3 to the 5th. Either one is correct. However, if I want to simplify, I probably want that exponent on the inside so I can simplify. Okay, square root of 3 to the 5th. Remember, it's a square root, and if we simplify a radical, we want to take out any perfect squares. Perfect squares means we have two 3's multiplied together. Okay, do we have any 3's? Well, we have 3 times 3 times 3 times 3 times 3. We have 5 3's. So this pair of 3's, that's a square root of 9. So I can pull a 3 out. Oh, I've got another pair of 3's. So I can pull that out. So times 3. And then I've got 1 3 left inside the square root. So I've got 9 rad 3. So this thing actually simplifies in simplified radical form to 9 rad 3. Let's try another one. Square root of x cubed. Whatever's on the bottom, that's the root you're taking. X cubed. Do we have a perfect square? We do. We have a square root of x times x times x. We've got 3 x's. 2 of them makes a perfect square. That's x squared. The square root undoes the squaring. So we have an x on the outside, x rad x. Okay. Now this one, cube root of x to the 4th. Okay, now careful here. It's a cube root. So we don't just need 2 of something inside. We don't just need a perfect square inside. We needed 2 of these, which made a perfect square. We need 2 of these, which made a perfect square, to be undone by the square root. But now it's a cube root. A cube root undoes a perfect cube. So now we need 3 of something. Do we have 3 x's? We do. We have 4. So we can take 3 of them. That's x cubed. Cube root of x cubed, those undo each other, and you just have an x on the outside. Now there's one x left inside of your cube root. Now make sure you tuck that 3 in there so it doesn't look like x cubed times the square root of x. Okay, maybe tucked it in too much, but better to tuck it in too much than not enough. Okay, let's look at the next one. This entire thing is raised to the 1/2, which means I'm taking the square root of the entire thing. Okay, now it's a square root. We need perfect squares. So I'm just going to spell it all out. I'm going to break everything down. 4 is 2 times 2. A to the 5th, A times A times A times A times A. There's 5 of them. Times B times B. A perfect square is anything times itself. So we've got a 2 squared. We knew that was a 4, so we can pull out a 2. We've got an A, we've got another A. We've got 2 pairs of A's, an A squared and another A squared. We square root both of those, we get A times A. We've got an A squared on the outside. And we've got a pair of B's. Square root of B squared is B. And then underneath the square root, we're still left with the only thing we didn't get to take out was this one A that was left over. Okay. All right. They get really fun when you have negative exponents that are also fractions. So let's go through the rest of these. 2 to the 3/5. So that's the cube root of 2 to the 5th. We need a perfect cube. We do. We have a perfect cube, 2 to the 3rd. So we can pull a 2 out. And then the cube root. Once we pulled out a perfect cube, we were left with 2 more 2's. So 2 times 2 was left inside. A 2 times the cube root of 4. Okay. All right. Here's where they get fun. Now we've got an exponent that's both negative and a fraction. Deal with those things one at a time. Let's deal with the negative exponent first. 1 over x to the positive 1/2. Remember, when you have a negative exponent, you have to move the entire power to the bottom and the exponent becomes positive. Okay, now we have to turn it into a radical. Remember our instructions at the beginning. Transform to radical form and then simplify. So that's 1 over the square root of x. Okay, we know simplified form, you don't want a radical in the bottom, so we're going to multiply by rad x over rad x. That gives us rad x times x. So now we have a perfect square in the radical on the bottom, which gives us just an x in the bottom. On the top, we have a rad x. Perfect. There's our answer. Okay, but now we have to think about this. What does that mean when it's a cube root in the bottom? So here we have x to the negative 1/3, or 1 over the x to the positive 1/3. or 1 over the cube root of x. Okay, you might think, oh, multiply by square root of x over square root of x. But that only works for square roots. We need to get rid of the radical in the bottom. And in order to get rid of a radical that's a cube root radical rather than a square root radical, we need a total of 3 x's under the radical. We only have 1, which means we need 2 more. So we have to multiply by the cube root of x squared. Remember, it's a clever form of 1. So anything we multiply on the bottom, we have to multiply on the top because we're multiplying by this thing. Anything over itself is 1. So on the top we get, remember fractions, multiply the tops, cube root of x squared. And on the bottom we have a cube root of x to the third. So those cancel each other out and we just get an x on the bottom. And now we got rid of the radical on the bottom. Okay, we're going to do 3 more of those. So if you didn't quite catch everything, it's okay. You can rewind or let's look at the next one. 2 to the negative 5/4. Again, there's an exponent that's a rational number and an exponent that's negative. Let's deal with the negative first. So 1 over 2 to the positive 5/4, which becomes 1 over the 4th root of 2 to the 5th. Okay, now here we do have 5 of something in the bottom. I'm sorry, 4 of something. It's a 4th root, so we need something to the 4th. Well, we have that. We have 1 over the 4th root of 2 times 2 times 2 times 2 times 2. We have 5 of them. It's a 4th root, so we need a perfect power, like 4 things multiplied together, which we have. That can cancel out. We can pull a 2 out on the outside. And what's left on the inside is a 1, 2. Okay, but again, we have a radical in the bottom, which is a problem. So we have to multiply by something to get rid of the radical in the bottom. 4th root of, but we don't just need 1 more 2. It's a 4th root, so we need 4 of something. We need 4 2's. We have 1, so we need 3 more 2's. 2 to the 3rd. So on the top, we have the 4th root of 2 to the 3rd, 4th root of 8. And in the bottom, we have 2 times the 4th root of, these two can combine, the 4th root of 2 to the 4th. Well, the 4th root and 2 to the 4th cancel each other out, and you're just left with another 2. So we've got the 4th root of 8 over 2 times this 2, so 4. Okay, let's do 2 more. I might run out of space. So this one, this goes down to the bottom. 1 over 3 to the 9/5, which is 1 over the 5th root of 3 to the 9th. Okay, we need 5 3's. We have 5 3's, so I can pull out a 3. When I take 5 of those 3's out, I'm left with 4 more of them. So the 5th root of 3 to the 4th. Let's bring that up here. 1 over 3 times the 5th root of 3 to the 4th. It's a 5th root. We need 5 of something. We have 4 3's, so we need 1 more. So the 5th root of 3 over the 5th root of 3. There's my clever form of 1. On the top, I've got the 5th root of 3. On the bottom, I've got a 3 times, and this thing becomes the 5th root of 3 to the 5th, which means I can now pull out another 3. I've got 3 times 3 on the bottom. On the top, I've got the 5th root of 3. Okay, one last one. 1 over x to the positive 7/4, or 1 over the 4th root of x to the 7th. Okay, we need 4 x's. I've got 4, so I can pull out an x. After I take out 4 of those, I've got 3 left, so it's still a 4th root. I've got x cubed. Now, I want to take out another one because I don't want a radical in the denominator. So I need 1 more x. So I'm going to multiply by the 4th root of x over the 4th root of x. And I'm left with 4th root of x on the top. I've got this x, and now Combining these, I've got the fourth root of x cubed. That gives me another x, and I've got an x squared. Okay? All right. So that's just an aside. That comes up here and there. But let's go back to these. I think you can work through these. I'm not going to work through all of these. I will work through them and post the solutions. But I want to move on to also post solutions to this page also. But go a few more pages. I don't think it's numbered. It was 127, 128. This one, the skills practice 37, we'll come back to. It's extra practice. Answers are down here at the bottom, so feel free to use that as extra practice. I want to focus on, and not the next page, we're going to come back to that, but this page, a few later. It says practice 7-4. I'm going to pick a few of these problems to do. These are some really good practice problems that are going to practice all the things that we just learned, okay? And I've got answer key. I will post an answer key, but there's a few of these I want to go over together. If you don't need to go over them, you can stop the video here, work through these. I'm going to go over a few of these. Okay, so let's look. 27 to the 1/3. Simplify each expression. Assume all variables are positive. Sometimes you can turn them into radicals. Sometimes you're simply going to simplify and leave them with rational exponents. One trick that helps quite a bit, and there's always sometimes multiple ways to do these problems. If you've got one of these numbers, remember when I said that there was that page of powers, powers of 2, powers of 3, perfect squares, perfect cubes. Sometimes you can recognize these, and that can make everything so much easier. Okay, a couple ways to do this. 27 to the 1/3. Well, that's the cube root of 27, which is 3. Another way to think about this, you can call that 27. If you break that down into a power of a smaller base, well, that's 3 cubed. 3 cubed is 27. It's being raised to the 1/3. 3 raised to the 3rd raised to the 1/3, a power of a power. You multiply the exponents. 3 times 1/3 is 1. So you would just get 3. So another way to do the same exact problem. Okay, let's try that with this one. 81. Now, if you know your powers, you would know 81 is 3 to the 4th. So I've got 3 to the 4th. That's my 81. It's being raised to the 1/4. And that's all going to be raised to the 4th. Okay. So what happens there? You get 3 to the 4th raised to the 1/4 raised to the 4th. So you can multiply all three exponents. 4 times 1/4 is 1. 1 times 4 is 4. So I get 3 to the 4th, which is 81. Okay. You might be thinking a power of a power. I could have just multiplied that 4 times the 1/4 and got 1, and I'm left with 81. That's fine. 32 to the 1/5. Well, I know there's multiple ways to think about these. Let's just sometimes try. I want to show you different ways. But a power of a power, you can multiply the exponents. 5. The 5th power of 32 to the 1/5 is going to be, you can multiply those exponents and just get 32. And 256 to the 4th raised to the 1/4, you just get 256. By multiplying the exponents, 7 to the 0 is 1. Okay, 8 to the 2/3. Now that 8 we can write as 2 to the 3rd. 2 to the 3rd is 8. Raised to the 2/3. Power of a power, multiply the exponents. 3 times 2 over 3. 3's cancel, you get your base raised to the 2nd, or just 4. -1 raised to the 1/5. Okay, let's think about that as a radical. That's the 5th root of -1. Now you might think, I can't take a radical of a negative. But no, that's not true. You can't take a square root of a negative. Because remember what a square root is, something multiplied by itself to give you that number. Now we can't take two numbers and multiply them by themselves, multiply a number by itself and get a negative. But if we're multiplying by itself 5 times to get this number, well, that can be negative. Okay? If you have a negative number multiplied by itself 5 times, you get a negative. This actually ends up just being -1. Think about that. That means what number multiplied by itself 5 times gives you -1? Well, -1 does. -1 times -1 times -1 times -1 times -1 gives you -1. Okay. Now this one's kind of the same. We've got the cube root of -27. That's because that 3 is on the bottom. Cube root of -27, and then after you do that, you're going to square it. Now, is there a number multiplied by itself 3 times to give you -27? Well, there sure is. -3 times -3 is 9, times -3 is -27. So the cube root of -27 is -3, and you square that, and you get 9. 16 to the 1/4. Okay. Easiest way to think about this, sometimes put that number 16 into a smaller base. 2 to the 4th raised to the 1/4. Power of a power, multiply the exponents, and you just get 2 to the 1st. Okay, this one, x to the 1/2 times x to the 1/3. Well, you're going to leave the base alone. 1/2 plus 1/3, add your exponents. I usually will go off to the side to add my exponents. 1/2 plus 1/3. Okay, so that's 3/6 plus 2/6, and I get 5/6. Notice here, it doesn't specify to leave your answer in any specific form. You don't have to leave it in radical form. You can leave it in as a power with a rational exponent. Okay, so here you've got the 2. That's y to the 1st. Y to the 1st times y to the 1/2. So 2y to the 3/2. Again, I'm just going to continue talking through these. Feel free. You don't have to watch all of this if you want to do it and just check your answers at the end. I'm going to continue doing a few more. Okay, so this gives you 8 to the 2/3. I usually like to write a number as a smaller base. 8 can be written as 2 cubed, and then raise that to the 2/3. Multiplying your exponents, you get 2 to the 2nd, or 4. Next one, 3.6 to the 0 is just 1. 1/16 to the 1/4. Let's see. You could do 1/2 to the 4th. A lot of times I just want to, well, I could do 1/2 to the 4th. And now if I want to move that power to the numerator, I've got 2 to the -4th. Move the entire power up, and the exponent becomes negative. Remember, that's still being raised to the 1/4. So multiplying your exponents, I get 2 to the -1, or 1/2. Again, not the only way to do that problem, just one way to think it through. These, I like to put them in the smallest base possible. So 27 is 3 cubed. 8 is 2 cubed. And I'm raising the entire thing to the 2/3. Remember, power of a quotient. So I've got 3 to the 3rd. I'm going to raise that to the 2/3. I've got 2 to the 3rd, and I'm going to raise that to the 2/3. So on the top, I'm going to get the 3's cancel because you're multiplying those. So 3 squared is 9 on top, and then 3's cancel again. 2 squared is 4 on the bottom. Okay. I'm not going to continue with all of these. The video would be really long. But let's go down. I want to talk about maybe one of these at the bottom. So write each expression in radical form. Okay. So some of these with negative exponents, we just did a bunch, but you might see something like this. T to the -2/7. So that's 1/t to the +2/7, or 1 over the 7th root of t squared Okay, 1 over the 7th root of t squared. Okay, now notice we have a radical in the denominator, so we want to simplify that. It's a 7th root, so we need 7 t's. We only have 2 t's. How many more t's do we need? Well, we need 5 more. So the 7th root of t to the 5th, 7th root of t to the 5th. So we get 7th root of t to the 5th on top. On the bottom, we're going to have the 7th root of t to the 7th, which is just t. Okay. And what else? Yeah, there's this one here. We could do this one. Because when you have this as a decimal, sometimes you have to turn that into a fraction. So we have a to the negative 1.6 or a to the negative 16 over 10. And then we can reduce that. A to the negative 8 over 5. Which is 1 over a to the positive 8 over 5. Or 1 over the 5th root of a to the 8th, 5th root of a to the 8th. Okay, so first of all, we can simplify. We need 5 a's. We have 5 a's. So we've got 1 over a, and what's left inside? 5th root of a cubed, 3 left after we take out 5 of them. Okay, now we want to get rid of the radical. We need 5 a's. We have 3. We need 2 more. So the 5th root of a squared over the 5th root of a squared. So on the top, we get the 5th root of a squared all over a. And this part gives us another a, because 5th root of a to the 5th. So we get an a squared. Okay. And what else? I think we're okay for now. I will finish this and post answer key to this page. I think this is a really good practice page. All right. Until next time.